So I believe this is a amino acid. Have you heard of amino acids in biology? And here we have a natural one and an unnatural one, whatever that means. So why is there an asterisk by this carbon? It is a stereocenter. It's asymmetric, meaning it's not symmetric. It means we have 4 different groups around this. And notice, so a line might be like a mirror image. We see this being a reflection of this one here. So we name these the same, 2-amino propanic acid, but only one enantiomer is biologically active. In aniline, only the left enantiomer can be metabolized by the enzyme. So we need a way to distinguish between these 2 molecules, and here's what chemists have come up with: the Cahn-Ingold-Prelog convention. Enantiomers have different spatial arrangements of the 4 groups attached to the asymmetric carbon. The 2 possible spatial arrangements will be called configuration. Each asymmetric carbon in the atom is assigned a letter R or S based on its 3-dimensional configuration. S is for left, which comes from the word sinister, and R for right, that kind of makes sense to us, meaning upright. Cahn-Ingold-Prelog convention is the most widely accepted system for naming the configurations of chirality centers. We assign a priority to each group bonded to the asymmetric carbon. Group 1 has the highest priority, Group 2 the second, and so on. Group 4 has the lowest priority, and we base this priority on atomic mass. Atoms with higher atomic mass receive higher priorities. If we have 2 carbons, we give a higher priority to carbon 13. Or if we have deuterium and regular hydrogen, and for the most part we know oxygen weighs more than nitrogen, and so on. So this looks like the model I had yesterday. So we look at the weights and assign this the highest, second highest, third highest, or lowest priority, second lowest. Once we've assigned our priorities, we can put the lowest priority group in the back, like this 4 goes in the back, and then we go 1, 2, 3. So I always used to like to call this a steering wheel, and we're turning the car to the right. Here shortly we'll go over another method. So here's the mirror image of this thing. You can almost see that if we put this one right over here, the red and red would be reflecting the pink and pink, and the blue and the green. So once again, we got to rotate and get that lowest priority group away from us. And then we go 1, 2, 3, and we're turning the car to the left. So it's an S enantiomer. So fluorine has the heaviest out of everything we're looking at, bonded to the stereocenter. Nitrogen, heavier than carbon, so it's number 2. Hydrogen's the lightest, so it's number 4. Now, with hydrogen going away from us, we can imagine a steering wheel. I marked, here's fluorine, here's the nitrogen, here's the carbon. And if we go 1, 2, 3, or 1 goes over to 2, and so forth, which way am I turning the car? Are we going to call this R or S? Now 1, 2, 3, we're turning the car to the left. So those little models are fairly straightforward. Eventually we're going to have a bunch of carbon everywhere, and it might be a little tough to figure out. We're probably going to add tiebreakers. In case of ties, use the next atoms along the chain of each group as tiebreakers. You might have to keep branching out till there's a difference, till the first point of difference. One atom of higher atomic number takes priority over the number of atoms. The multiple bonds are dealt with in this fashion. We treat double and triple bonds as if each were a bond to a separate atom. So let's say this R is my stereogenic carbon, and I'm trying to figure out what's bonded to this carbon. We can imagine that this carbon is bonded to a hydrogen, and it's bonded to a carbon, and then this double bond gets duplicated, meaning I can imagine another carbon bonded here. There's the first one with the first hyphen, and then the second one from the other hyphen, and then we can do the same thing with this carbon. So that's how we want to treat that. Here we see that again. This carbon is bonded to a hydrogen, nitrogen, and then another nitrogen. We can see that there. And then this nitrogen is bonded to a carbon, and the carbon from the double bond. So here's the model kit from the other day. We want to ask ourselves, what type of configuration are we going to assign to this carbon here? So wedges are coming out of the plane of the board. Lines are in the plane of the board. So it looks like I'm good to go here. Maybe to make things a little easier, we're going to draw what's attached. So I want to assign priority to all these groups. What has the lowest priority? Hydrogen. So I can label that number 4. What has the highest priority? Yeah, bromine, 79.7. So then I branch out and I see 2 carbons. Carbons are both 12. What am I going to do? So I tell students, make a list of what's attached. What's attached to this carbon here is 3 hydrogens. What's attached to this carbon? A hydrogen, and a carbon. So if it's a card game, this hand wins over this hand because we have an element that's higher. The numbers don't matter. All right, so this is number 1. This is going to be number 2, and this is going to be number 3. So if we go to the steering wheel analogy, I'm going from number 1 to number 2, and I'm turning the car to the left or the right. Right. So we call this thing R. We say this carbon has R configuration. Now there's a little better way to do this. You're all in physics, you know the right-hand rule. Never got that far. None of you were in physics or weird vector dot product things. Anyway, you can use your hands. And what you do is you take your thumb and you put that in the direction of the lowest priority group. So if I take my left hand and put my thumb going back and I curve around this way, I'm going 1, 3, 2. That doesn't look right. I take my right hand and I go 1, 2, 3. Looks like my right hand is curling in the direction of our priority. And that's kind of nice. So true or false, these are distereomers. These are mirror images which are non-superimposable, so they are enantiomers. Alright, so we just assigned a configuration to this enantiomer. We want to do it for this next one. Now the bromine is going behind the plane of the board, so that means my hydrogen is where it's coming out. And we already did all the work here to figure out what was going on. This is the highest priority, hydrogen's the lowest. And you'll get to where you just see, well, here's a methyl and here's an ethyl. This has got to have higher priority. So instead of the steering wheel, I take my hand and I say the hydrogen's going out. And then I curl my hand this way and it looks like 1, 3, 2. That's not sequential. So I take my other hand and I go 1, 2, 3. So, yeah, this must be the S configuration. And we might have figured out that if we've assigned this thing R, and we did it right, that means the mirror image has got to be, let me make that look like mirror image. If this one's the R, this one has to be the S. Alright, what do we think about this? Well, I think this is going to be a whole lot easier than what it could be, because hydrogen is our lowest priority group, and it's pointing away from us. Well, that makes it always easy with the steering wheel method, which is a little inferior to using your hands. Alright, so oxygen weighs more than carbon. Here's a carbon. Here's a carbon. Which carbon has priority? So I say to students, make a list of what's attached. What's attached to this carbon? I see a hydrogen, and there's a carbon over there. This, I see a hydrogen, and then I follow along that bond and I get to one carbon, and then we say it's duplicated due to the double bond. Two carbons beat out one carbon. So I'm going to give this number 2. I'm going to give this number 3. So this has a greater priority. So then I pull out my hand and I put it in the direction of the hydrogen and I go 1, 3, 2. That doesn't look right. Got to come over here with this hand. Thumb is pointing back. That's where the hydrogen is. And I curl my fingers around 1, 2, and 3. And I look at this hand and say, this is my other right. Raise your right hand. Raise your left hand, your other left hand. So that makes this with an S configuration. Which atom has the number 1? Yeah, this one here. Luckily, I got an answer here. So I might look at that carbon and say what's attached. There's the unwritten but understood hydrogen. There's this carbon over here, and then the double bond duplicates it. If I come up and look at this carbon here, there's 2 hydrogens, and then that carbon. Right, so I'm going to call this highest priority, and then what's the second priority? This carbon or that carbon? So I'll make a list of what's attached. We don't ever attach the asymmetric carbon. Alright, so this is going to have second priority. This will have the third priority. What has the fourth priority? That light guy, hydrogen. Right? So I'll do the old school way and say, here's my steering wheel. Looks like I'm turning it to the right, but my lowest priority is facing me, so I used to tell students, I'm turning the car, but the steering column's piercing my heart. With the lowest priority pointing at you, you do the steering wheel, you say it's opposite of that. Let's do the hand method. Thumb out, it's pointing towards me. 1, 3, 2. Doesn't look like it's working. 1, 3, 1, 2, 3. Alright, I got my left hand. So this must be S. So it looks like I'm turning the car to the right, and the steering column is going through my body. It's opposite. Now what? Alright, I did the easy part. I put my lowest priority group so I can see it. So I have 3 carbons. Which carbon's going to have the highest priority? So if I make a list of what's attached to this carbon, there's the understood but unwritten hydrogen. Then I go to a carbon and the double bond duplicates that carbon. If I come over here, I get to the same point. So in the slideshow it said you got to continuing branching out till there's a point of difference. I get over to this carbon, I'm going to say there's a hydrogen, over here there's 2 hydrogens, carbon. Over here there's hydrogen, carbon, and carbon. So here's my point of difference. So this is going to be number 1, this is going to be number 2, this one here is number 3. So 1, 2, 3, thumb pointing out. I'm going to have to call this R. So sometimes making the list of what's attached is good, but you can see these are tied. Then you move to here, 2 hydrogens, a hydrogen, and a carbon. So this beats out all the rest. 1, 2, 3. Might look S, but our low priority group is pointing at us, meaning the steering column's going through us. We don't like the steering wheel analogy. We go to this. We go 1, 2, 3. Thumb pointing out. One more example. Should be easier than the other. So we know this is our highest priority group. 2 carbons. Which carbon has priority over the other one? Well, this carbon has a hydrogen, It's bonded to an oxygen. The double bond duplicates it. This carbon has a hydrogen bonded to another carbon, and the double bond duplicates it. So probably didn't have to make that list to look at the oxygen and say this is going to be number 2, this is number 3, behind the plane of the board is number 4. So 1, 2, 3 looks clockwise. Looks like I'm turning the card to the right. I'll just check it with my hand. Put my thumb going back into the plane of the board. 1, 2, 3. One last example for us. The oxygen definitely is the heaviest. This carbon here is going to be... Oh, I can't have this. Sorry about that. I had an achiral carbon because it didn't have 4 different groups. Now this thing here has 4 different groups. It has a methyl, has a hydrogen, has an OH, has an ethyl group. So the oxygen's simple, it weighs more than the carbons. Here's 2 carbons. This one has 2 hydrogens and a carbon. This one just has 3 hydrogens, so this becomes number 2. This comes number 3. Of course, hydrogen is number 4. So if you can step over to the side and look, imagine this one coming out, this one being here. To me, it looks like it's going to be S. So let's use my hands and the thumb rule. I'm going to point my thumb in the plane of the board like so, and I can definitely imagine my fingers wrapping around. I'll start like this. Hydroxide, the ethyl, and then the methyl. So that looks like a good S configuration, right? Left hand. Any questions? Clear as mud, right? All right, that's a good place to stop.